In the silent depths of space, something extraordinary is growing. 700 million light-years away, nestled within the Abell 85 cluster, sits a titan that challenges our understanding of cosmic evolution. Holmberg 15A. Most galaxies are vibrant nurseries of spiraling stars, but this is a cosmic graveyard. It is a brightest cluster galaxy, the undisputed king of its domain. For billions of years it has acted as a gravitational vacuum, capturing and consuming every smaller neighbor that drifted too close. But at its core lies something far more extreme. Astronomers discovered a central void, so vast it defies theoretical expectations. Inside this hollowed-out heart sits a black hole 40 billion times the mass of our Sun, one of the largest ever detected. It represents a concentrated mass of staggering density, dominating a region hundreds of thousands of light-years across. We thought we understood the limits of what the universe could create. We were wrong. And before we start, like the video and subscribe to our channel, and let us know in the comments below where in the world you're watching from. We're always eager to hear where our viewers are tuning in from. Abell 85 is a massive galaxy cluster sitting nearly 700 million light-years away from Earth, and at its very heart sits the monster known as Holmberg 15A. To understand why this galaxy is so peculiar, we have to look at its classification as a brightest cluster galaxy, or BCG. In the vast architecture of the cosmos, galaxies are not just scattered randomly, they are pulled together by gravity into massive cities of stars. In these dense environments, the BCG is the undisputed king. It is almost always a massive elliptical galaxy that sits at the precise center of the cluster's gravitational pit, acting as a cosmic vacuum cleaner that has spent billions of years consuming its smaller neighbors. Holmberg 15A is the textbook definition of an elliptical BCG, but it exists on a scale that defies traditional logic. Unlike spiral galaxies like our Milky Way, which are flat disks filled with gas and dust to birth new stars, elliptical galaxies are shaped like giant swollen footballs. They are composed of ancient reddish stars that swarm around the center in disorganized orbits. Holmberg 15A has grown to its gargantuan size through a process called hierarchical merging. Over eons, dozens of smaller galaxies have slammed into it, their stars being absorbed into the larger structure. What makes this specific elliptical galaxy so fascinating to astronomers is its core. Usually, when you look at a galaxy, the center is the brightest part because that is where the star density is highest. However, Holmberg 15A has an incredibly faint and depleted core. It is as if something has hollowed out the center of the galaxy from the inside out. This strange emptiness is the smoking gun for its history of violent mergers. When two massive galaxies collide, their central black holes sink to the middle and begin a gravitational dance. As these two titans spiral toward one another, they act like a gravitational slingshot, physically kicking stars out of the galactic center and into the outer suburbs. This leaves behind a massive diffuse heart that belies the incredible weight of the object hiding in the shadows. While Holmberg 15A is the undisputed king of its domain, it first caught the attention of astronomers not for what was there, but for what appeared to be missing. When researchers began peering into the heart of the Abell 85 cluster, they expected to find a typical brightest cluster galaxy. Usually, these massive elliptical galaxies have a predictable structure where the density of stars increases sharply as you move toward the center. This creates a brilliant concentrated core that stands out against the backdrop of space. However, when the telescopes turned toward Holmberg 15A, the data told a strange and contradictory story. Instead of a piercingly bright center, this galaxy possesses an enormous, diffuse, and incredibly faint core. It acts like a hollowed-out shell, spanning a distance of nearly 15,000 light-years. To put that into perspective, this central region is larger than many entire dwarf galaxies. Early imaging showed that the surface brightness of this core was the lowest ever recorded for any early type galaxy. It was a massive central void that defied the standard models of galactic evolution. Astronomers were baffled because a galaxy this massive should have trillions of stars packed tightly into its heart, yet here was a vast region where the stars seemed to have been systematically swept away. This core scouring effect provided the first real hint that something truly monumental was lurking in the shadows. Scientists realized that such a giant hole in the stellar population could not be a coincidence. It suggested a violent history involving the merger of two smaller supermassive black holes. As these two titans spiraled toward one another, their immense gravitational fields acted like a cosmic centrifuge, flinging hundreds of billions of stars out of the galactic center and into distant orbits. This process left behind a depleted, darkened heart. The scale of this void was so unprecedented that it pointed directly to a central engine of unimaginable proportions. The sheer size of the emptiness suggested that the black hole responsible for this clearance had to be one of the most massive objects ever discovered in the history of humans observing the cosmos. This missing light is a cosmic fingerprint left behind by one of the most violent dances in the history of our universe. To understand why the center of Holmberg 15A looks like a ghost town, we have to look back at the chaotic sequence of events that built this empire. When two massive galaxies merge, their central supermassive black holes don't just settle down quietly. They begin a long, spiraling descent toward the common center of their new home. As these two titans draw closer, they create a gravitational tug-of-war that transforms the entire galactic core into a chaotic slingshot. In a healthy young galaxy, the center is usually crowded with billions of stars huddled together. But as the binary black hole system orbits, its sheer gravitational influence begins to physically kick the stars away. This process is known as core scouring. Each time a star wanders too close to the swirling pair of black holes, it is caught in their gravitational wake and flung outward at immense speeds toward the edges of the galaxy. Over hundreds of millions of years, this celestial eviction clears out the center, leaving behind a hollowed-out shell. In the case of Holmberg 15A, this scouring was more extreme than anything astronomers had ever seen. The low surface brightness we observe today is the direct result of that mass exodus. There are simply fewer stars left to shine in the middle of the galaxy because the central black hole, which grew to 40 billion times the mass of our Sun, has functionally depopulated its own neighborhood. What remains is a massive, dim void that spans thousands of light years. It is a region of space that has been stripped of its brilliance, serving as a dark monument to the power of the monster lurking within. This lack of light isn't a sign of emptiness, but rather a sign of gravity's ultimate triumph over stellar density, leaving us with a core that is hauntingly quiet and impossibly vast. To truly understand the invisible giant lurking within Holmberg 15A, astronomers turn to one of the most powerful instruments in our arsenal, the multi-unit spectroscopic explorer. Mounted on the Very Large Telescope in Chile, this sophisticated device did far more than simply take a picture of the distant galaxy. It acted like a high-speed prism, breaking down the light from every individual pixel into a detailed rainbow of information. By capturing thousands of spectra simultaneously across the entire hollowed-out core, the instrument allowed researchers to map the movement of stars with surgical precision. This technique revealed something staggering about the velocity dispersion within the galaxy center. In a typical galaxy, stars move at predictable speeds based on the collective mass of the visible neighborhood. However, within the heart of Holmberg 15A, the stellar motions were chaotic and incredibly fast. The data showed that as stars moved closer to the center of the void, their speeds increased dramatically, whipped around by a gravity wells far stronger than the surrounding starlight could explain. This high-velocity dispersion is the smoking gun for a supermassive black hole. The stars were not just drifting, they were being flung around at hundreds of kilometers per second, reacting to a gravitational pull that outweighed tens of billions of suns. The spectral lines analyzed by the researchers showed a distinct broadening, a phenomenon that occurs when some stars are moving rapidly toward us while others are moving rapidly away within the same line of sight. This stretching of light confirmed that the core was not empty because it lacked matter, but rather because it had been scoured clean of slow-moving stars. Only the most energetic, high-velocity stars could survive the environment without being consumed or ejected. By measuring these frantic orbital speeds, the team could work backward to calculate the mass of the central object required to keep such fast-moving stars in orbit. The result was a jaw-dropping figure of 40 billion solar masses, confirming that the central engine of this galaxy is one of the most concentrated and terrifying concentrations of mass ever discovered in the cosmos. To weigh a shadow 40 billion times the mass of our Sun, astronomers had to look at the motion of the ghosts left behind. They utilized a highly sophisticated mathematical framework known as Schwarzschild orbit superposition modeling. This technique does not just look at a single star, but instead treats the entire galactic center as a complex web of thousands of potential stellar paths. By using high-resolution data from the Very Large Telescope, the team mapped out how stars were whipping around the invisible center of Holmberg 15A. The process begins by creating a virtual library of every possible orbit a star could take within the galaxy. These models account for the visible light from stars and the invisible pull of dark matter, but they require a massive central point of gravity to make the math match reality. The researchers plugged the orbital velocities of these stars into their equations, testing different masses for the central black hole until the model perfectly mirrored the chaotic high-speed movements observed in the telescope data. What makes this specific discovery so groundbreaking is that the team did not rely on traditional scaling relations, which often estimate mass based on the size of the galaxy itself. Instead, they used these direct orbit models to prove that the gravity at the center was far more intense than anyone had predicted. The math revealed that the sheer emptiness of the galactic core was actually a footprint left by a monster. The more stars that were missing from the center, the larger the black hole had to be to have cleared them out. By calculating the energy required to kick billions of suns out of the core, the Schwarzschild models confirmed that only a central mass of 40 billion suns could explain such a colossal void. This direct measurement turned Holmberg 15A from a mathematical curiosity into one of the most significant gravitational anchors ever discovered in our observable universe, proving that sometimes the weight of the darkness is best measured by the speed of the light that remains. To truly grasp the scale of Holmberg 15A star, we have to place it alongside the undisputed heavyweights of the cosmos. For years, the black hole at the center of the galaxy, Messier 87, was our gold standard for cosmic terror. When we captured its orange glowing silhouette in that historic first image, its 6.5 billion solar masses felt incomprehensible. Yet compared to the monster lurking in Abell 85, Messier 87 looks like a mere satellite. Holmberg 15, a star, is more than 6 times heavier. If you placed it at the center of our solar system, its event horizon would reach out far beyond the orbit of Pluto, swallowing every planet, asteroid and moon we have ever known into a dark, frozen abyss. Then there is TON 618, the current title holder for the most massive black hole ever discovered. At 66 billion times the mass of our Sun, it technically outweighs Holmberg 15, a star. However, there is a fundamental difference in how these two giants exist. TON 618 is a distant quasar, a relic from the early universe fueled by a frantic, blinding feast of gas that makes it one of the brightest objects in existence. Holmberg 15, a star, by contrast, is a sleeping giant. It has already finished its meal. It sits in the quiet, hollowed-out center of a massive elliptical galaxy, having physically shoved its neighbors away to claim its territory. But the most shocking metric isn't just the mass, but the density of the footprint it leaves behind. While it may not be the heaviest by pure weight, the way it dominates the space around it is unparalleled. Most supermassive black holes are proportional to the stars in their host galaxy, but Holmberg 15, a star, is an anomaly. Its mass is nearly 10 times larger than what astronomers expected based on the galaxy's luminosity. It is so incredibly dense and influential that it has created the largest core depletion ever observed in the known universe. It is a silent, invisible titan that has carved a hole in reality so large that even the light of hundreds of billions of stars cannot fill the void. This cosmic giant was not born in a single moment of creation. Instead, the galaxy we see today is the product of a violent and prolonged history of galactic cannibalism. Over billions of years, Holmberg 15A acted as a gravitational trap at the center of the Abell 85 cluster, relentlessly pulling in smaller neighboring galaxies into its massive embrace. Each of these collisions was a transformative event that reshaped the structure of the galaxy. When two massive galaxies merge, they do not just blend their stars together, they bring their central supermassive black holes into a deadly orbital dance. As these two gravitational titans began to spiral inward toward one another, they sank to the very center of the newly combined system. This process happened over and over again as Holmberg 15A swallowed up its peers. The merging of multiple galaxies played a critical role in concentrating an unimaginable amount of mass into a single point. Every time a new galaxy was consumed, its central black hole would eventually find its way to the core, eventually merging with the existing resident to create a singular, growing behemoth. This sequence of mergers is exactly what allowed the central black hole to reach the staggering weight of 40 billion solar masses. It was not just a simple accumulation of gas and dust. It was a series of catastrophic unions that funneled matter and dark matter into the heart of the cluster. These mergers also explain the unique hollowed-out shape of the galactic core. As the black holes from the intersecting galaxies circled each other, their immense gravity acted like a cosmic broom. They interacted with any star that wandered too close, swinging them away at high velocities and scattering them into the outer reaches of the galaxy. Without this history of multiple successive mergers, the core would still be packed with dense clusters of light. Instead, the relentless cycle of galactic integration turned Holmberg 15A into a laboratory for extreme physics, resulting in a dark, empty void dominated by the heaviest single object ever measured by human observation. To understand how this cosmic exodus happens, we have to look at the violent history of the galaxy itself. When two massive galaxies collide, their central supermassive black holes do not simply sit still. They begin a long, spiraling dance toward each other, drawn together by their own immense gravity. As they move closer, they form what astronomers call a binary black hole system. This pair begins to act like a gravitational blender at the very heart of the new merged galaxy. As these two titans orbit one another, they pass through dense clouds of stars that have lived in the galactic center for eons. When a star wanders too close to this binary pair, it does not always get swallowed. Instead, it experiences a phenomenon known as the gravitational slingshot. The star is caught in the intense, shifting gravity of the two orbiting black holes and is accelerated to incredible speeds. The binary system effectively robs the star of its original path and flings it outward with such force that it is launched into the outskirts of the galaxy, or sometimes right out into intergalactic space. For every star that is kicked out, the two black holes lose a tiny bit of their orbital energy and sink slightly closer together. This process is the core scouring. Over hundreds of millions of years, the binary pair acts like a mechanical pump, systematically clearing the center of any stellar material. In a typical galaxy, the core is the brightest and most crowded region. But in Holmberg 15A, the black holes were so massive that they essentially emptied their neighborhood. Eventually, the two black holes merged into the single 40 billion solar mass behemoth we see today. But the damage was already done. They had successfully ejected a mass of stars equivalent to several entire galaxies. This creates the hollowed-out look that defines this giant elliptical galaxy. What remains is a dark, cavernous void where the most concentrated light should be, leaving behind a ghost town of a core that serves as a permanent architectural scar of the most powerful gravitational interaction in the known universe. To truly grasp the sheer scale of the Holmberg 15A black hole, we have to look far beyond the boundaries of our own neighborhood in space. While 40 billion solar masses is a number so large it almost loses its meaning, the physical footprint this monster occupies in the fabric of spacetime is even more terrifying. If you were to place this black hole at the center of our solar system where the Sun currently sits, its event horizon, the point of no return, would not just swallow the inner planets like Mercury and Earth. It would consume everything we have ever known and continue expanding outward into the dark. The radius of this black hole is estimated to be around 790 astronomical units. To put that into perspective, Pluto sits a mere 39 astronomical units from the Sun. This means the event horizon of Holmberg 15A is 20 times larger than the entire expanse of our solar system out to the Kuiper belt. If you were sitting on the edge of this black hole's shadow, the Sun and all its orbiting planets would be nothing more than tiny specks of dust drifting deep within its light-trapping belly. It is a sphere of darkness so wide that light itself would take several days just to travel from the center to its edge. Even Voyager 1, the furthest man-made object ever launched, has only traveled about 160 astronomical units over the course of nearly 50 years. It would have to travel for another 2 centuries just to reach the boundary of this single object. We are talking about a physical structure that is large enough to contain dozens of solar systems arranged end to end. This is not just a heavy object, it is a geographic anomaly in the cosmos. It represents a volume of space where gravity has become so absolute that it defines the architecture of its entire host galaxy. When we call it the densest or most massive, we are describing a leviathan that makes the vastness of our own planetary system look like a microscopic grain of sand in a desert of infinite night. When we talk about the density of a black hole, we are usually faced with a paradox. Traditionally, as a black hole grows in mass, its average density actually drops because the volume of its event horizon expands much faster than the matter being added to it. However, Holm 15 a star flips the script when we look at the sheer concentration of mass within a finite region of space. It is not just heavy, it is one of the most efficient gravitational anchors ever measured in our cosmic history. With a mass of 40 billion suns, this behemoth has a Schwarzschild radius that spans nearly 800 astronomical units. To put that into perspective, that is several times the diameter of our entire solar system, reaching far beyond the orbit of Pluto and deep into the interstellar void. While the internal density of such a giant is technically low by mathematical standards, its physical influence is anything but dilute. This object represents a concentration of 40 billion stars worth of matter packed into a single singular point. In the vast, lonely stretches of the Abell 85 cluster, there is nothing else that packs this much gravitational punch into such a relatively tiny footprint. What makes it the densest in a practical sense is how it dominates its environment. Most galaxies have a central bulge where mass is spread out across thousands of light years in the form of gas, dust, and stars. But in Holm 15a, the core has been scoured clean, because those twin black holes from ancient mergers slingshotted almost every star out of the neighborhood. Nearly all the mass of the galactic center is now concentrated purely within the event horizon of this one monster. In most large galaxies, the central mass is a cocktail of dark matter and stellar populations. Here, the central mass is almost 100% black hole. It is a terrifyingly pure concentration of gravity. When astronomers look at the scale of this object compared to the empty, hollowed-out void surrounding it, they see a density of influence that is unmatched. It is a dark, heavy heart that has swallowed the very essence of its galaxy, leaving behind a ghost-like shell where only this 40 billion solar mass anchor remains, holding the entire cosmic structure together through sheer concentrated power. Holm 15a is more than just a graveyard of stars. It is a vital blueprint for understanding how the scaffolding of our universe is constructed. This ultramassive black hole serves as a relic from a chaotic era of cosmic history, teaching us that the most gargantuan structures in existence are not born but forged through relentless violence. When we look at this 40 billion solar mass behemoth, we are seeing the end result of a multi-billion-year game of galactic billiards. It reveals that the growth of galaxies and their central black holes is an inseparable lockstep dance. In the early universe, smaller galaxies collided to form larger ones, and their central black holes followed suit, sinking toward the center and merging in events that shook the fabric of space-time itself. The sheer scale of the void at the center of Holm 15a proves that black holes are not passive passengers within their host galaxies. Instead, they are the primary architects of their environment. By ejecting billions of stars to create that hollowed-out core, the black hole actively reshaped the galaxy's evolution, effectively shutting down the formation of new stars in the center and dictating the ultimate shape of the entire stellar population. This tells us that there is a fundamental limit to how much a galaxy can grow before its central engine begins to push back, carving out its own kingdom. Furthermore, Holm 15a challenges our previous models of how much mass a single object can actually accumulate. By reaching 40 billion times the mass of our Sun, It suggests that the potential for black hole growth in the centers of massive galaxy clusters is far higher than we once suspected. It forces us to reconsider the scale of the first generation of black holes and how quickly they were able to feed on the surrounding gas and dust. This galaxy is a window into the extreme physics of the deep past, proving that the most massive structures in the cosmos are defined by the invisible giants lurking at their hearts, proving that to understand the largest things in the universe, we must first master the physics of its densest points. While the discovery of Holmberg 15A has redefined our understanding of cosmic giants, astronomers are only beginning to scratch the surface of these galactic centers. To truly peer into the heart of brightest cluster galaxies and witness the gravitational dance of 40 billion suns, we need a new generation of eyes on the sky. The current data from the Very Large Telescope has been revolutionary. But the future of black hole hunting lies in facilities that can resolve the fine details of stellar movement at distances of hundreds of millions of light-years. The first major leap forward will come from the Extremely Large Telescope, currently under construction in the Atacama Desert. With a primary mirror spanning 39 meters, it will be the largest optical telescope on our planet. Its power lies in its ability to correct for atmospheric distortion using advanced adaptive optics, allowing it to see the universe with 16 times more clarity than the Hubble Space Telescope. When aimed at the centers of massive elliptical galaxies, the ELT will be able to track individual groups of stars orbiting deep within the core. This precision will allow researchers to weigh black holes that are currently too distant or too quiet to measure, potentially revealing giants even larger than the one found in Abell 85. Complementing this ground-based power is the James Webb Space Telescope. While it is famous for its stunning images of nebulas, its infrared capabilities are a secret weapon for studying galactic cores. Dust and gas often shroud the centers of galaxies, blocking visible light and hiding the mechanics of core scouring. The James Webb can peer right through this cosmic fog, mapping the distribution of ancient red stars that were left behind after the binary black holes finished their gravitational cleanup. Further into the future, the Nancy Grace Roman Space Telescope will provide a wide-angle view of the cosmos, helping us identify thousands of new galaxy clusters. By spotting cores that appear unnaturally faint, it will provide a treasure map of targets for more detailed follow-up studies. These upcoming projects are not just about breaking records for mass or density, they are about understanding how these apex predators of the universe shape the history of every galaxy we see today. We are standing on the threshold of an era where Holmberg 15A will no longer be an outlier, but a window into the evolution of the cosmos itself.